With Teresa, like
2 hours.
2 hours. Gross. What's an hour and 45 minutes?
Eat a grilled cheese.
Bro, you're gonna go with us to Muji?
Hey.
That's what I said. I asked if we could take different cars.
All right, so let's talk about indirect reference homework first of all. So I'm recording this lecture also because some people aren't here because they're at WSU or elsewhere, and we're going to be talking about like prep for the finals. So I want to make that available for everybody. So I'll post a link to this. All right, so homework 13, which was the one I just gave back. So you're using indirect addressing to look at registers 0 through FF and count the number of registers that were equal to 0. And most people had the right idea. They were using generally FSR 0 and then starting that at 0, counting up to FF, or starting it at FF and counting down to 0, and then checking INDF 0 to see if it's 0 and adjusting a count. So there's this thing called a fence post problem. This pops up all the time in computing. I don't know if fence post problem is the best term. You're using fence posts to delineate sections of land or something, right? And we have 1, 2, 3, 4 sections marked off here, but we have a total of 5 lines drawn, right? We have 1, 2, 3, 4, 5 lines splitting off 4 sections. So when you're trying to code something and you're trying to do something n times, depending on the specifics, sometimes you want to loop up to n, sometimes n minus 1, sometimes n plus 1. Similarly, sometimes you want to loop until some value is less than some target, or until it's less than or equal to some target, or greater than or equal. And there's this edge case that always pops up as to should it be n minus 1, should it be n plus 1. And it pops up again and again in programming. So it popped up a fair amount on this assignment. In this case, we're trying to we're trying to analyze registers from 0, 0 through FF. Right? If we go into decimal, this is registers 0 through 255. We actually need to loop 256 times to do this. Right, even though our highest register is only 255. So we can do something like this. Initialize FSR 0 to 0. We can do whatever we're going to do with INDF 0. So in this box, I'm encompassing checking INDF 0, looking to see if it's 0, and if it is, incrementing the value in WReg. Right, all that sort of stuff. And then we need to move to the next file register, so we're going to increment file select register 0. And we need to know if we should go back to the top and do some more. So what condition should we check in here? There's a lot of possible answers. Oh, stay high level. Just plain old pseudocode. What condition should we check for?
You could check if FSR 0 has reached FF.
And if it's not, then we want to loop.
Yeah.
So this was a solution a lot of people came up with. The problem is, if you run through this and you look at the edge case at the end, suppose FSR 0 is FE. Okay, so we're going to check that file register, do whatever we're supposed to do, increment it to FF. FSR 0 is FF. If it is, we're going to exit. We haven't actually checked that last file register. right? So we're exiting one spot too soon. So what we can actually check in this case is if it's equal to 0, 0, if we're just checking an 8-bit register. Because if it's an 8-bit register, it'll be equal to FF. We'll deal with that register. We'll increment it. It'll go back to 0, 0, and that'll cause us to exit right here. And it starts off at 0, but before the first time we check, we're going to increment this to a 1. So it'll start off with 0, we'll process 0, it'll be a 1, we'll go ahead and loop, we'll process 1, increment 2, go ahead and loop, right? And then the last one will be FF, we'll process FF, increment to 0, and that'll kick us out of the loop.
Well, I guess you can't check start 0, right? Check out just
Yeah, so this is pseudo-ish code. We could check FSR0L to see if it was 0. Or we could also say, we could check FSR0 high, bit 0, and see if that's a 1. Because if we're incrementing using post-inc, which is what most people did, which was awesome, when we increment from 0, 0 to FF, and then we increment once more, the low byte will go back to 0, but the high byte will increment to 1. So you can use that also. Similarly, if you're decrementing, you can start off with FSR0 equals FF. We can say decrement. And then in most cases, you said if it's equal to 0, let's exit. Well, in this case, if you check for 0 here, you're going to exit your loop too soon. Because you just checked register 1, you decremented this to a 0. This is equal to 0. If you exit at that point, you didn't actually check register 0. So here you probably want to actually check to see if it's equal to FF again. So that's just detail. I took off 1 point for that just because I didn't want to do fractional points. It's a really minor detail and has nothing to do with indirect addressing per se. It's just something to be aware of, and if you're going on into more CS courses after this, that's just one of those gotchas that comes up again and again. And the most important thing is knowing that it's there, right? And then how do you nail this down? Well, instead of doing it 256 times, try to do it 3 times and figure out what your logic has to look like. And then you can actually loop through it on paper in your head and make sure it's doing it the right number of times. Does that make sense? All right, so other things that I saw in here, which may or may not have cost points. ClearF W is not going to do what you want it to do. Okay, ClearF is an instruction that expects a file register, and W is not a file register. W is a symbol which is set EQU to 0. So ClearF W will actually clear file register 0, which is usually not what you're after. If you want to actually clear the file register, you can say ClearF WReg. Okay, WReg is the official name of the file register that contains or corresponds to the W register. And I think that's F84. It's not F84. It is F something something FE8. So WReg is EQU to FE8. So this is just like saying ClearF 0xFE8. The other option would be something like move literal 0 into W. So that's always available. All right, the other thing, suppose we want to do something like this. We want to initialize something to be FF, right? Let's say we want to set some variable count equal to FF. So what does this instruction do in our program?
Nothing.
It doesn't really do anything, right? It's not an instruction, it's an assembler directive, so it doesn't generate any code, it doesn't translate into any code. All this does is says whenever I use the variable count, replace that with 0xFF. So now if I say decrement file count,
XFF gets there.
that's the same thing exactly as decrement 0xFF. What's the value of that file register? No idea. Unless you load a value into it, we don't know what the value is. And this does not load FF into the file register called count. Right? The file register count is stored at location FF in the file register memory. But we haven't put a value into there. If I want to actually load the value FF into there, I need to do something like this. Move the literal value FF into W, and then move W into the file register count. Right, that actually initializes it. And there are some cases where people were trying to initialize things to 0 or to FF or to other values, and they were using EQU. Really easy mistake to make, and it's a ruthless one because you don't get any messages from the compiler or the assembler.
Is pound define the same as using EQU?
Yeah, pound define is basically the same. There are differences. I've never quite made peace with exactly what the differences are. Pound define is actually a lot more powerful than EQU. All right, any other questions on that indirect homework? Okay, so that looked really good, and there'll be a question that'll involve indirect addressing on the final. So I think you're good for that. All right, so homework 12. Take your group number, multiply by 2, and then increment if you're after your lab partner, divide by 53, round to 2 digits. Okay, so that gives you a pseudo-random number. That should be hopefully different for each person. And then your goal is to convert that into IEEE 754. So any questions up front about that, first of all? So I had some suggestions on here on how to write it out, but let me clarify, because you'll see some floating point questions on the final. Suppose you're asked to convert this number into IEEE 754 floating point, right? Here's what you should ideally be doing. You need to convert the left side and the right side into binary. Okay, you need to change this into a binary number, ignoring all the floating point business, just straight binary powers of 2. Okay, so 5 is 101. If it's a bigger number, you can go through the algorithm of dividing by 2 and looking at remainders and so on. Engineering 250 exercise, right? Come up with the binary equivalent of 5. Bless you. And check your result, right? Because if this is wrong, your whole answer is going to be wrong. And it's not going to be wrong by just a little bit. Okay, it's going to throw everything off. So check your answer. 1 plus 0 plus 4, that's 5. All right. And annotate that somehow to separate it from all your work. Okay, 0.75. Well, let's do this times 2 equals 1.5. 0.5 times 2 equals 1.0. All right, and I'm done, so I'm going to look at this piece, and so I'm going to say 0.75 equals 0.11000 with a bunch of zeros. And annotate that piece clearly. Okay? The idea here is if you do something wrong, if you get the wrong value when you convert to 0.75, everything else is going to be off. Okay? But if whatever value you wrote down here, if you did everything right after that, I'd like to be able to know that and say, okay, you lose 1 point because you divided by 2 wrong, right? But if I don't know clearly what you were starting with and I see the wrong answer, unless I can easily follow your work, you lose most of the points. All right, so now I'm going to put these together. 5.75 equals 101.11 with a bunch of zeros. And don't do it on the side here where it's buried in other stuff, right? Put this down so you've got paper that's organized in portrait instead of landscape. Okay? And this is times 1, which is 2 to the 0. So the way I learned to do this in school might be different for you. Move the decimal point. Going to move it over 2 spots to the left. When I move over to the left, my number is getting smaller. There's 101 point, now it's 10 point, now it's 1 point. So my number here is getting smaller. This number has to get bigger. So I moved 2 spots over. Let's bump up the exponent. By 2. And you can sanity check here, right? This is 4. This is something between 1 and 2, so the product is something between 4 and 8, which is where this number falls. If I multiply this out and I get something between 0.1 and 0.05, I know I did something wrong. All right. Mark that clearly. All right, so what do we have? Our exponent is equal to 2. Our fraction is 1.0111 with a bunch of zeros. And our sign is positive. Okay, you're marking your work along the way, so that it's really easy for somebody to say, the final answer is wrong, okay, this is right, this is right, this is right, oh, this is wrong. Right, pinpoint the error, and then know how to go from there. All right, now you want to pack it into your IEEE format. So make yourself a template. This first bit's going to be a bit corresponding to the sign. This is going to be 8 bits corresponding to the exponent plus 127. Okay, that's what the bias of 127 means. It means you're going to take the exponent, add 127. That's the 8-bit number we put here. And this is the fraction after the decimal point. So our sign bit is 0. Our exponent plus 127. Exponent was 2, so this should be 129. Which is that, and the fraction after the decimal point would be 0, 1, 1, 1, and then a bunch of zeros. All right, and circle that, because that's almost your final answer. If I ask you to put it in hex, you need to break this into hex. Start from the left, because you know this is the most significant bit. Break it off in chunks of 4 until you get through 32 bits. And this is where many mistakes happen. So 0, 1, 0, 0 is 4, 0, 0, 0, 0 is 0, 1, 0, 1, 1 is B, 1,000 is 8, and everything else is 0. So there's your final answer. So I strongly recommend when you're doing these, right, lay it out logically. Everything that you have to do to get to the answer, make sure that's written down on the paper. Okay, just so that it's easy to give partial tribute. All right, does that make sense? So people were doing these on the board, and questions 1 and 2 didn't look bad. I mean, people were basically getting the right answers, right? It's just keeping straight all the details. Whatever you got for 10, your answer for minus 10 should be exactly the same, except the first bit becomes a 1 to indicate negative. Everything else stays the same. If you do question 6, when you convert 0.01 into binary, you get this repeating decimal, just like 0.2 for that first question, right? So I asked question 7, does it surprise you that 0.01 can't be represented exactly, and what are the possible implications of this? So what do you think about this? I mean, as humans, we can write 0.01 exactly with a finite amount of ink. It's just 0.01. 3 strokes and a dot. On a computer, you can't do that. You would need an infinite number of bits to represent it. So what are the possible implications of that?
A lot of lost money.
A lot of lost money, yeah. Think office space, right? You can't represent a penny exactly. Depending on which way you round, if you try to add a penny to a balance, it's going to be slightly more or slightly less. If you do that 100 billion times, that's potentially, you know, a lot of money.
Is that what they did in the movie?
Yeah.
They were trying to trim the pennies off of something, and they moved the decimal point the wrong way. So the first day they made, like, I don't know, $80,000 or something.
It was like 80 million.
80 million.
It's too much.
Yeah. So this was a problem, right, when computers were first being used. Using floating point representation like this or some other format doesn't always get you an exact value, even for something as simple as 0.01. So a lot of times in finance, the computers won't use this kind of floating point representation. They might use something like fixed point notation, where you just store everything in pennies, and now you can use integers. Now that doesn't work today because, you know, we do fractions of pennies and so on. But it's something that needs to be accounted for because rounding errors can accumulate. Another thing you can do is what's called binary coded decimal. And we've talked about this briefly. So let's say we have a number 3.25. And we want to store that in binary. Well, we write 4 bits for the number 3. We write 4 bits for the number 2. We write 4 bits for the number 5. There's our number. And we just understand that there's a decimal point sitting before those first 2 digits. It's just another way to store numbers. It's not right or wrong. As long as we know this is what we're doing, it'll work perfectly well. But it complicates addition. Because if I try to add 3.25 and 3.25, I'd like to get 7.5, right? What do I get? 1 and 1 is 0. 1, 1 and 1 is 0. 1, 0, 0, 1, 0. 0, 1, 1, 0. Which looks like 6.410. Because 1, 0, 1, 0 is the number 10. And that's not right by any measure. So if I use binary coded decimal, right, BCD, and I do an addition operation, I need to do something else. I need to make an adjustment. I need to look at each column, and if it's bigger than 9, I need to add an extra 6. It's just a thing. Yeah, so if digit is bigger than 9, then add a 6. So I would add 0, 1, 1, 0, and I don't need to adjust these. And so now I get 0, and 1, 1 is 0, 1, 1 is 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, and there's my 6, and there's my 5, and there's my 0. So if you come down here and you look at your instructions in table 20-1, there's an instruction called DAW. which is decimal adjust W register.
Free.
Basically says look at the 4 least significant bits. If it's bigger than 9, go ahead and add 6. Or if there's a carry bit set, go ahead and add 6 to W. That's exactly what this instruction is for if you're doing binary coded decimal arithmetic.
I see.
So you add digit by digit, and then you do a decimal adjust W register. Store that result, and DAW will update the DC register. So DC is the decimal carry register. It says you had to carry out of bit 4, which takes care of this fact that I had a 1 carry out of here, so I had to add an extra 1 on this next digit. So that's built in there. Even though it's a reduced instruction set, they spent an instruction to do niceties for us if we do BCD arithmetic. So you don't need to know how to do that, but I wanted to mention it because it's a thing.
So is floating point precision like a current research topic, or is that something that we've just kind of accepted? That
I think it's pretty well understood at this point. I don't fully understand it, but I think it's pretty well understood by others.
kind of falls into that NP category.
Yeah, there always is error, and so let me show you the calculator I was using last week in class. So we can put in 0.2, and it'll convert it to hexadecimal for us. But it'll also show us the actual value that was stored, which, as you can see, is slightly bigger than 0.2. And the error is off at the 9th or 10th decimal place. Right? So, I don't know if we have an option for 64-bit. Yeah, I don't know how to use this. But yeah, I think we've mostly made peace with it, and if you're doing something that really needs absolute precision, then we use something like BCD. COBOL, a really early language back from the 60s, I believe, which was used a lot for finance and accounting and things like that, had BCD as basically a native data type. So you could say, I want these numbers to be stored in a fixed point notation, and it would work with those.
Do we not use COBOL anymore?
Some people do. A lot of people did at the turn of the century because there were all these legacy programs written in COBOL that had been running for half a century, and nobody knew if they were going to break when the clocks turned. And so a lot of COBOL programmers got kind of resurrected from retirement to vet code.
Nice. Do you think banks use COBOL?
Yeah, somewhat. COBOL's a fun language. It's a language where you almost get to write like in full sentences. You can name your variables crazy, ridiculous things, and instead of semicolons at the end of sentences, you have periods. So it's like you're writing like, your novel or something.
US Banks uses something like, it's super DOSy. It's crazy.
Yeah, there's a lot of stuff out there.
US Bank is crazy. Don't work for US Bank.
Yeah, I've worked for banks before. I'm good. All right, so question 3. So this was something to think about. How would you sketch an algorithm to multiply 2 floating point numbers? So did anybody think about this? What did you come up with? What kinds of things?
We're talking about multiplication right now?
Yeah.
So you would have to add the exponents.
Mm-hmm.
Maybe a lot of the other stuff that we talked about.
Okay.
But adding the exponents was one big thing, and then doing bit by bit for everything.
Yeah.
You would want to have like to multiply them by like, have them all in base 10 so you could add the exponents together, right?
Well, you can add in any base. But for us, let's just think about scientific notation, because IEEE 754, it's really just scientific notation for computers, right? It's really a sign bit, it's a fraction multiplied by 2 raised to some power. So let's just think about scientific notation. Suppose we have 5 times 10 to the 5th, and we have 3 times 10 to the 7th. And we want to multiply those. Well, as you said, add the exponents. We're going to get something times 10 to the 12th. And we can multiply the fractions. We're going to get 15 times 10 to the 12th. That's pretty easy, right? We gotta, if we're doing IEEE, we gotta subtract 127 from the exponents, and then we gotta add it at the end and stuff like that. But basically, we're adding the exponents, we're multiplying the fractions. There's one small detail, which is this is not a properly normalized scientific notation. Right? Scientific notation, we're only supposed to have one thing before the decimal point, so we would need to write this as 1.5, and since we move to the left, we need to increase the exponent. But it's not a bad algorithm. Take the exponents, unbias them, add them together, rebias them, multiply the fractions, and then maybe move the decimal point one spot to the left or the right. Probably to the left, if at all, and adjust the exponent. There's a few other edge cases. If we multiply something by 0, we need to get 0, and if we just do this, we're not necessarily going to get 0, because 0 has a particular representation. So you got to check some special cases, but by and large, it's not too bad. All right, so what about addition? So this is a harder problem, right?
You want the exponents to be the same.
Gotta have the exponents the same. And we could do that a few ways. We could change the 5 times 10 to the 5th to be 0.05 times 10 to the 7th. Or we could change the 3 times 10 to the 7th to be 300 times 10 to the 5th. Once the exponents are the same, we can go ahead and we can just add the fractions. And then we have to renormalize again. So this one turned out to be normalized already. This one we have to move the decimal point, adjust the exponent. So again, 3.05 times 10 to the 7th. But it's a fair bit more work. And in some cases, we don't have to do anything. All right, 5 times 10 to the 25th plus 2 times 10 to the negative 30th. Well, if we try to turn this into something times 10 to the 25th, it's going to be a really, really, really small fraction. And when we add it to 5, it's going to be 5 plus some really small fraction times 10 to the 25th. Right, but this is going to basically turn into 0 when we try to add. So there's more edge cases to deal with. And the renormalization at the end isn't usually just a single digit, right? It could be something huge. For example, if we do subtraction, 5 times 10 to the 14th minus 4.999999 times 10 to the 14th. Well, they both have the same exponents, so we don't need to move anything around, but when we subtract, we're going to get this crazy unnormalized number, and then we need to move the decimal point and adjust the exponent accordingly. So your renormalization becomes more complex too. So how do you do this? You write a bunch of code.
You just do it.
You just do it. You take your numbers, you break them apart, you get the pieces of them, you do the operations, right? If you find the exponent that's smaller and see how much smaller it is than the larger exponent, and then move the decimal point that many places in that piece's fraction, and then you add the fractions as just plain old integers, and then you renormalize, and so on and so forth. And you got to deal with the sign bit, right? So if the sign bit of the second number is negative, you know that you have to do a subtraction, and so on. So those get a little weird. What do you do with the sign bit for multiplication?
XOR it.
You knew that.
Because it's not an AND.
Yes.
That's why I know.
So you're multiplying two numbers with sign bits. So 0 is positive, 1 is negative. So positive times positive should be positive, that's a 0. Positive times negative is a 1. Negative times positive is 1. And two negatives multiplied together give you a positive, which is a 0. So you want your sign bit of the product to be just the XOR of the two sign bits. So there's another chance to use an XOR. So that's just stuff to think about. One of the exercises in the book for this chapter asks you to actually write the algorithm and pick assembly language. That's pretty cool. That's a good, like, rainy weekend project maybe, but it's fairly intense. But yeah, in software you basically just do it. Now in hardware, that's a whole other story. If you want to build a circuit to do floating point multiplication, that's a beast. Imagine trying to build a circuit like in a 250 lab that does all of those steps we just talked about. Yeah, it's pretty crazy. I have one on my YouTube channel with good music.
One that you did?
Yeah, for cell matrix. I'll pull it up at a break. All right, so any questions about floating point stuff? And we've stuck with single precision. If you want to do double precision, it's really just this last step where you're taking your sign bit, your exponent, your fraction. You add 1023 instead of 127. You have 11 bits instead of 8 bits, and you have more bits in the fraction. And so when you break it into 4-bit chunks to write in hex, you get a different set of values. But it's fundamentally the same thing, right? Different bias. More bits for the exponent, and everything else is identical. All right, cool. So speaking of multiply, there are a pair of multiply instructions available on the PIC processor. You can say multiply W with a literal value, mul LW. It's like an add LW or an I or LW. It's just a multiply LW. It takes a literal value from 0 to 255 and multiplies W by that value. When you multiply two 8-bit numbers, you potentially get a 16-bit result. Right? It's generally something bigger than what you can fit in 8 bits. So these multiply instructions don't put the result back into W. They don't put the result in a single file register. They put the result in a very special pair of file registers called product high and product low. It's just two other file registers, and the only thing they're used for is for storing the result of a multiplication operation. So if W is equal to 10, and I say mul LW 100, 10 times 100 is 1,000. If I look at product H and product L, I'll see a 16-bit representation of the number 1,000. So you can do multiplication on the PIC. It's pretty easy. So you can multiply W by a literal, or you can multiply W with an 8-bit file register, mul WF. And again, the result goes into a pair of product registers. So those are useful to know if you're doing math. Lost my index. All right, so one other thing I want to mention. And this is definitely not on the exam. But we know that in the PIC processor we have two memories. We have the file registers, which go from 00 to FF, and then there's these special function registers from F80 to FFF. And these are the things that we increment, we compare, we add, and so on and so forth. But there's a whole separate memory, which is program memory. And this is where we store our instructions. And they're physically separate banks of registers. It would be cool, so we know we can write instructions that read and write the contents of file registers. It would be cool if we could write instructions that could also read and modify the contents of the program memory. Because then we could write programs that modify themselves. Not just modify the data, but actually modify the instructions. And we can do that.
It's the Matrix.
It's the Matrix. There's a new Matrix movie coming.
Yeah, I saw that.
Yeah. So chapter 6 on the data sheet talks about this. It's flash programming, flash program memory. So there's these table read and table write instructions that basically let you load up a table pointer. It's a special function register with a value, and let you load a data value into another register and then say write that data value into that memory location. Okay. Now program memory is 16 bits wide. So we're dealing with something bigger than bytes, and the addressing of program memory is 21 bits typically. So 3 bytes to specify the instruction's address. So there's a lot of mechanics going on here. So the table pointer is table pointer low, high, and upper, same as usual. And table latch is an 8-bit register that gets the contents of a byte in memory. So if you want to read, you can load up table pointer and you can say read, table read star instruction. It'll load the value of table latch. If you want to write, you load a value into table latch, you load a value into the table pointer, and then you do table write star, and it'll write the contents of that latch into memory. But it's a tricky thing to do because you don't want to do this accidentally. If you accidentally change the value of a file register, not a big deal. If you accidentally change the value of your program, that's a big deal because when you reset, your file registers basically are scratch. But your program memory remains from power cycle to power cycle. So if you accidentally change your program and you pull the power off and you power it back up, it's got the corrupted program still in memory. So they make it hard to accidentally change the values of these things. So you have to go through a handshake. And this is part of why we're not getting into this in more detail. But you got to do all of these things. Load the table pointer with the address of the row being erased. Set the econ1 register for the erase operation. Set a write enable. Disable interrupts. That's important. Then you have to write a 55 to econ2. Then you have to write an AA to econ2. That's your secret handshake. Then you set the write bit, and then the CPU stalls for the duration of the erase, and then you can re-enable interrupts. Okay, that's for erasing a value. So what's magic about 5 hex and AA hex? This is something that you get for free in here. What's 55 hex look like in binary?
0, 1, 0, 1, 0, 1.
Good. What about AA?
1, 0, 1.
What the heck? Yeah, that's what I thought.
Yeah.
I was like, am I crazy?
Which makes sense because A plus 5 is F. So if you add these, you get FF, which would be all ones.
Wait, but why don't you just do FF?
Because what if you have something that's stuck at 1? If something was accidentally stuck at 1 and you were required to write FF, you might be trying to write something else, but something's stuck at 1, so it comes out as FF. Or maybe it's stuck at 0, and so you try to write a 0, but it's stuck at 0, and so it's a 0 anyway. So what's happening here is you're writing something, and then you're toggling every single bit and writing those other values again. And you could write 0, 0, and FF, but what if something has gone wrong where all the bits are forced to the same value? So this is a whole nother science art form of digital logic, is testing, right, and designing for reliability and so on. And you'll see these patterns pop up a lot in quirky situations, like where you're doing something and you need a secret handshake. You might use them when you're sending information on a communication channel and you want to know that you've got a good communication going. You would require the person sends you a 5 followed by an AA. And almost the only way that's going to work is if all 8 bits are able to send 0s and 1s independently. So it's just a handshakey thing, but you'll see those pop up a fair amount because of that. So they're good ones to kind of internalize. So there's your program for erasing something from Flash, and then to write, you have to go through all of this stuff. So a simple 16-step procedure. And it takes about 18 milliseconds to do 64 bytes. So if you want to have fun with something and you're stuck on a desert island with a PIC processor, right, you can dig into this stuff. And writing code that modifies itself is fun. It can get you into all kinds of interesting spaces. You want to write a loop, you can just put a go-to, but you can test something, and when some condition happens, you can change that go-to into a pair of no-ops and break out of the loop that way. All right, any questions on the lab? Lab 6, a bunch of people got it done already. So we talked through it last time. Okay, so you'll keep working on that. All right, so let's take a 5-minute break, and then let's talk through the final exam and talk about what we've done and what you might expect to see on the exam. Is there any interest in spending an hour after class from 4 to 5 going over stuff? Most people came in this morning, and I put that in for you. Anybody still need an hour after class?
I think I'm
You good? Okay, so I won't plan on sticking around, but I'll be in lab. All right, so take a 5-minute break, and then we'll go over the final exam.
Scared Nick.